It's like that. And you all know that we are not good at this part, because that's what you always experience about weather forecasting. You know, cyclone is coming. Only day before yesterday they got it wrong. They said it's going to come here and there will be huge deluge and cities will be underwater, and that is a fodder for, of course, 24 hours news channel. And in fact, one of this commentator made that this is the only profession that they are right means wrong 99.9%, and next day they still have the job. This is a very interesting profession. So what happens? We cannot track the trajectory of a vortex. It's that bad. Why? Because our weather forecasting grid. Even today, the most sophisticated model, global circulation model, would come with 1.5 kilometer by 1.5 kilometer. So what happens as a consequence? There are places like small countries like Singapore which does not even get one node for itself. So they of course take it from the surrounding, and then they do micrometeorology and find out how to predict the local weather in a local time framework. But this dispersive nature of structures, fluid dynamical structures, is a real fact that we'll have to keep in mind. So this equation has this unique property. It does not dissipate, it does not disperse. So you generate your numerical test yourself. I'm sure Dr. Bhumkar would have set up a lot of experiments during your afternoon hours. He will show you, he will teach you hands-on how to do these things and find out. Okay, so suppose say your initial condition is written like this. So at the mth node at time t equal to 0, the solution is prescribed like this. So it has a spectrum u naught of k. K is the wave number, means number of waves per unit length, in 2 pi, sorry. In 2 pi length, how many waves you have, that is called the wave number k. And you have to do this Fourier transform, because you are talking about most generic problem. Do not be trapped by spectral methods, because they always talk about periodic problem. But your generic fluid dynamical problems, engineering problems, are neither periodic nor homogeneous. So you should think in terms of inhomogeneous non-periodic problem, and then you, of course, you don't have the luxury of dealing with Fourier series. You should be handling Fourier transform. So if I have this as my initial solution, at a subsequent time Tn, I could write down the solution like this. And what you would be noticing that the exact solution at Tn would be simply will be equal to Ik within bracket xm minus Tn, Ctn. C is this velocity. So basically that's what happens, that whatever the initial condition you give at a later time, you will find it at x minus Ct. That's it. So this is one of the interesting, simple, yet challenging aspect of this. And we are talking about resolution, right? What is resolution? Resolution is something is that when you are computing with a finite resource computer, you cannot resolve all the wave numbers. Theoretically speaking, you should be going from minus infinity to plus infinity, which you cannot. So what you do is you go from a computer-defined Kmax minus Kmax to plus Kmax. What is this? This is called the Nyquist criteria. So per wave, you need at least 3 data points. So 3 data points per wave means 2 delta x will give you 1 wavelength. So what's the wave number? K is nothing but 2 pi by lambda. That's what I said, that's the definition. So k is 2 pi by lambda. So lambda itself is the minimum wavelength that you can resolve is 2 delta x. That's what I said. If you choose delta x, that fixes my range of k. And this is what is called as the Nyquist criteria. So unfortunately, whenever we are computing, we are not going from minus infinity to plus infinity. Instead, we are going to do this from minus k max to plus k max. Now, suppose I am evaluating space derivative with respect to x, let's say du dx, then what we can do, any method. This is what I will make a observation. I'm sure Professor Bhumkar would give you some handout if he has not already done. There you will see how this C matrix can be found out for any method. You know, when we started doing it, we work in finite difference, but we also characterize other methods like finite volume, finite element, spectral method. That all comes into the same thing, provided we know the C matrix. So at a later time, I will share with you a paper that we wrote a few years ago for different methodology, how to calculate the C matrix and what are the consequences. But let's say we know it. So please accept my statement that we can write this equation for any method. Then what you can do, you realize that what we had done before, we wrote ux like this. So if I take a derivative of this quantity with respect to x, then what happens? I will just simply multiply this whole thing by ik. So that will be our Fourier spectral method. But mind you, this is not in the sense that what we understand by Fourier spectral method, because we are still talking about Fourier transform, not Fourier series. Okay? But taking a derivative in spectral method would be equivalent to multiplying this amplitude function by ik. Now when I go and do it by any generic method which has this corresponding C matrix, then what happens is I do not get ik, but I get so-called ik equivalent. So every method has a k equivalent. That's the main story. You have a finite element method, I can tell you what the k equivalent would be if I am taking a derivative, and if I take a finite volume method, then also I'll do it. So what happens is, then I will write it symbolically as ik equivalent, and in the previous transparency I showed you in terms of C matrix, and that would be something like this. Ik equivalent at the jth node will be 1 upon h, should be multiplied by this. I have the C matrix, so if I'm looking at the jth node, then what I do, I look at the jth row of the C matrix and multiply by all the u vectors. So because that's the way the equation is. This is something interesting. Please do understand. I think that's where I lose people. Like if I am doing a derivative here, then what do I get? Ik in this. And what about the phase? Phase is exactly where you want it. But when you do write like this, what does it mean? This is a C matrix, this is a u vector. So all the nodes are required in defining the du dx at the jth node by looking at the jth row multiplied by the whole of u column. That's what we meant, right? That's what we are doing. Now, as a consequence, what happens is, although I am looking at the derivative at the jth node, theoretically speaking, all the nodes are taking part in a discrete computing. But the Fourier spectral method says, no, you need only information from jth node only. So what we do is we do a little bit of a trick. That's what you have seen here. That, well, there's a minus sign missing. So there is a minus sign there like this. So you project the lth u vector into the jth point. So that is equivalent to just simply writing e to the power ikxl. Then I subtract minus ikxj and I add plus. So that's what happens. So this is like a projection operator that projects all the lth node to the jth node where you are looking at. And then you go back to your convection equation, plug it in. What you would notice that you will get an equation of this kind. This is known to most of us who are in computing. We call this as Courant-Friedrich-Lewy number or CFL number. Right? So what it says that differential change in U is proportional to the CFL number. The way I discretize my space derivative and project it to the jth node. That's all there is to it. And if you, let's say, are doing Euler time integration, that means what? You have a solution at time tn and you want to go to tn plus 1. In Euler time integration, what happens? This du is nothing but u at n plus 1 minus u at n. And that you are dividing by u of n. So this will be nothing but u of n plus 1 divided by un minus 1. So u of n plus 1 by un is what we call as numerical amplification factor. And that is what I can do is I can put that minus 1 on this side, then it becomes plus 1, and this quantity itself is NC, and these things are as there. Right? So you realize that your numerical amplification factor is given by this. It is very apparent for you that you won't use it. Why? Because you look at the modulus of G. What happens? See, you are marching from Tn to Tn plus 1. And the ratio un plus 1 divided by un. According to this equation, it should be equal to 1 because it's non-dissipative.